Hello everyone and welcome back to this next lecture in the DC to DC converter series, and this is where we had left off in the previous lecture where we had simulated the 3-winding transformer. So specifically we had simulated this 3-winding transformer in an isolated environment, so just providing any random voltage and checking out the voltages in the other windings, that is winding 2 and winding 3 where loads are connected. So just to recap, these are the voltages that we had achieved. So these are the currents and these are the voltages. So as you can see, we had achieved a transformation, and also most importantly, by adjusting the duty ratio of the third winding, we had produced a negative voltage with respect to winding 1 and winding 2. So this therefore solves our problem. We now have a multi-winding transformer which we can use for the forward converter. In this lecture, I'm going to use this transformer and insert it into the simulation of the forward converter. So let me close this down and let me go back. As always, before I start this lecture, a little bit of brief background that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I have full-length online courses on the MOOC website Udemy, and for that all you have to do is go over to my own website, which is pythonpowerelectronics.com. that is pythonpowerelectronics.com, the name of the circuit simulator, and this is the home page. In the home page, just check out this button, Learn. In this Learn button, these are all my courses. So I have several courses. I have courses which are basic courses on how to simulate circuits using Python Power Electronics, which also involves little basics about Python and installing Python Power Electronics. I have another course on using digital signal processing in power electronics. In this course, I talk about how you can design filters such as low-pass filters and notch filters using Python packages like Signal, which is included with SciPy. And if you're interested more on the magnetic side, I have another course on how to simulate magnetic components such as inductors, coupled inductors, and even transformers using Python Power Electronics. And I have a case study of how to simulate a flyback converter with several outputs. The other course which I have is more on how you can design and analyze controllers using Python for power electronics applications. And here I have taken the specific case of a single phase grid connected converter connected to a single phase grid. And of course, the very latest course which I have is a free course which is more on what are the opportunities available in the power electronics domain. So this course is not really for experienced power engineers. It is more for very young undergraduates or even high school students who may be wondering what to specialize in as they go further in their careers. So this is a completely free course. All these courses are hosted on the MOOC website Udemy. All you have to do is click on this button to get the course link. So the links for these courses are provided in the description of this video. If you don't want to check out this course, this website, check out the description for this video as well. So with this, I'll return back to the simulation. So in order to use this transformer, I need a few things. So for example, in this circuit, which is a test circuit, I will be using this circuit of the transformer in the forward converter. That's number one. Along with this, I also need the parameter file, because remember, every circuit is associated with the parameter file. The next thing is we need the control file. So we have this control file, which currently is in this 3-winding transformer directory. We'll be using this mathematical model. And in addition to the mathematical model, I will also export the descriptor for this control so that I can directly use this descriptor in the forward converter. So let's go and do all these. So I just have to go back to the main page and I go to Edit Circuit Parameters and I go to 3-winding transformer. And here I'll have to just click on this button, Export Parameters. This will export all the parameters of this particular circuit file as a .csv file, which is known as _params.csv. Right? So this gives us the latest parameters of this circuit. So with that, we can go back And now I go to my edit control page. And in the edit control page, I need the descriptor for this transformer model, because this is a mathematical model of the transformer. So let me go to configure control, and here I will pick up all of these, because this is where I changed and added the third winding to this particular control file. So therefore with this I'll have the updated descriptor for my 3-winding transformer. So again, all I have to do is just click on export control, and this will export an _desc.csv file. So with this we are good to go. So we don't need anything else. I'll just go back to the simulation and click on the forward converter. So now the first thing which we need to do is I would like to close all these files down, because we'll be now opening these files in the forward converter directory. So let me close this down as well, and let me go to my file browser. So this is where we are. Now, as I said, I'm going to pick out the transformer winding, the parameter file for the transformer, the mathematical model of the transformer, which is transformer model.py, and the descriptor file for this particular transformer, right? So I'm going to copy all these, go to my forward converter, and I'm going to paste it here, right? And it will complain, it will say these windings, these files exist. I'll just replace them, because I now have updated files anyway. These were old files. So with this, now we have an updated forward converter simulation. So always remember, this does not mean that they have already been included. I have to re-import them into my simulation. So let me go and do that. So the first thing which I need to do, I need to go back to add circuit file, because remember, I have changed the actual circuits themselves, right? So which means always click on process circuit schematics. Whenever you make any topological change, it is absolutely essential that you click on process circuit schematics. It is possible we might have a mismatch and there could be some error. There is none in this case, but it's always possible. So with this, we are now good to go. We can go back. Now we need to re-import the parameters. So for example, I go to view components in my 3-winding transformer, and here I can upload the parameter file. So make sure you're in the right directory. This is not the right directory. Go to forward converter, and here choose the _params.csv file. So click on it and click upload. So with this, we now have the changed transformer parameters. For example, you will see it here. You will see that these are all the new parameters. For example, you will see the polarity has been adjusted. The third winding has an opposite polarity with respect to winding 1 and winding 2. And the same goes for the control voltage sources as well, right? The positive polarity of winding 3 is reverse that of winding 1 and winding 2. So you can just confirm this yourself. So with this, we are good to go. And now that we've done with this, we need to edit the control file. So we don't have a control file at all, because remember, we stopped at this stage and we had gone directly to the 3-winding separate directory where we had created a test box for our 3-winding transformer. So here, make sure you're in the right directory, add the transformer model.py. I'm just going to call this transformer model, magnetic model. Save it, configure control, choose upload file, and I just have to choose the descriptor and click on upload. And now just go through, we now have all the parameters of this control file, right? You can just verify it yourself. These are all the new parameters. Most importantly, they should contain the winding 3 variables. That is most important. So with this, we are good to go. Let's go back to the main page. Now remember, we also need a gate signal, because remember, we have a forward converter. This will not do without a gate signal. So make sure there is a gate signal. There is no gate signal. So let's go and pick up a gate signal from one of the other ones. Let's say from flyback converter. So I'm going to go click on the gate signal and the descriptor file and copy it into the flyback forward converter. So this is now my gate signal. So let me go over to my editor, make sure I have the right files. I'm going to close this down because I don't need this directory anymore. And here, let me go over to the forward converter and let me open gate signal. And let me also open the transformer model just in case. And you see we have all these. Now with gate signal, just have to make sure that we have a modulation signal which is fairly decent. So we have chosen a modulation signal of 0.1. Right? So let me just increase this to, let's say, 0.3. Right? 0.1 is very small. We can even increase it to 0.3 or 0.4. So with this is good enough. This is S1 gate. Most important, make sure that this S1 gate is hooked up to our output control. So let's go over here to configure control and make sure that control output, not actually we don't have a control output yet. We'll have to do the control output in the gate signal.py file. So this can be added in the gate signal itself. So with this is good enough. We now have a gate signal generator. That is, we now have to generate PWM signals for our switch because the forward converter does have a switch. Without having a gate signal, we cannot run the simulation. In the transformer model, I would like to make one change. And that change is, I would like to change the rating of the third winding to be equal to that of winding 1. Because the reason is, this third winding has to supply energy back to the DC voltage source when the switch is turned off. And for that, it'll be better if we actually have this at the same rating. Right? For now, this is good enough. Again, this is a design parameter which we can also tune, but I don't want to do about that now. Let's just have this so that we can run the simulation. Now that we have this, let us add this other file into it as well. So let me go, make sure you're in the right directory and choose gate signal.py. And I will just call this PWM generation. Click on the save control file. To configure it, let us choose the descriptor file, make sure in the right directory, and choose the _desc.csv file. Click on upload, and we get all this. So there's not much, as you can see. What's most important is this S1 gate is indeed connected to the output target, which is output S1, switch S1. And if you want to confirm, let's go here and make sure that the voltage source, which is the source of this forward converter, has a switch S1. Right? And it's important to do this because remember, we are actually mixing two simulations. It is quite possible in such cases that we might have a mismatch between components. Right? So this is good enough. Now with this, we are almost done. We are ready to simulate. Right? Now, if something is left out, the only way to know is to actually run the simulation. So let's go over to view output. Actually, before that, let me go over to the edit simulation parameters. Make sure your integration time step is small enough. Right? Do not choose something like 10⁻⁻⁶ or 1 microsecond for the simple reason that we are now simulating at 1000 Hertz. Alright? Technically, a forward converter should be working at a much higher frequency. Right? Recommended frequencies of operation for a forward converter range anything from 10 kHz to around 50 kHz. The reason why I'm running it at such a small frequency is because otherwise the simulation takes a long time. So just to hasten the simulation or speed up the simulation a little, I'm choosing a low switching frequency. If you are simulating watching this video, I would suggest that you choose something much higher like 20,000 Hertz, right? Or 20 kHz. That's good enough. That's a more realistic frequency for a forward converter. And make sure that the transformer model, the rated frequency is also the same, so that you have realistic parameters for the transformer. So with this, we are good to go. The moment the truth has arrived, we click on run. It says the simulation is running, but always go to the command line and make sure there is no error. And as you can see, there is no error. So this simulation is running. Since this lecture has already gotten pretty long, I will end this video right now. In the next video, we will plot the results of the simulation and analyze the performance. So once again, if you have any doubts about what I said or what I did, or you're simulating along with me and you want to do something else, please do post either in the comments or send me an email or message me on social media, whichever is your preference. Otherwise, I will see you next week where we will continue with the simulation. Thank you so much for watching and see you soon. Goodbye for now.